Good evening, all present here.
Sorry, ma.
We are now
Okay.
about to begin the Day 6 Session 11 of ATAL Online FDP on Quantum Intelligence, Integrating Quantum Technology with AI and ML. This session 11, the speaker of this session is Dr. Ritojit Majumdar, and the topic to be discussed is fighting with noise in a quantum computer before error correction. Dr. Ritojit Majumdar is a research scientist at IBM Quantum, based at the IBM India Research Lab. He is a part of the quantum algorithm and engineering team where he collaborates with researchers to attain utility scale results using IBM quantum technologies. He holds a PhD from the Indian Statistical Institute, during which he spent a significant period as a visiting scholar at the IBM Thomson J. Watson Research Center in New York with the prestigious Fulbright Nehru Doctoral Research Fellowship. Prior to his doctoral studies, Dr. Majumdar served as an assistant professor at BP Poddar Institute of Management and Technology, affiliated to Maulana Abul Kalam University of Technology, and continued his academic engagement there as a visiting faculty member during his PhD tenure. He is a recipient of the gold medal from the Calcutta University for his master's degree, and he was honored with the esteemed DST Inspire Fellowship. In addition to his work at IBM, he is currently a guest faculty at the Department of Computer Science and Engineering at Calcutta University. May I now request Dr. Majumdar to begin his session.
Yeah, thanks a lot for the introduction and thanks for having me here. It's a pleasure to be here in this FDP. And this is the last day, I guess. If I remember well, this is the last day. And I saw some of the very good talks that you all of you had throughout the lecture, and the ones who will talk after me today are also my seniors. So I'm sure you are having a great experience here. So what I will discuss about here today, let me share my screen and uh, get started. So as the topic suggested, what I will discuss about is fighting with noise before error correction in a quantum computer. So whatever applications that you are going to run on a quantum computer, whatever things that you are interested in, say machine learning, say optimization, chemistry, physics, any type of problem that you are interested in, some application oriented problem that you are interested in, to run them on quantum computers. Current quantum computers have noise. So we will discuss this in more detail, but just to come up with a setting of what we are going to discuss. If we have noise, if we have error in the quantum computer, the natural ask will be that we should be able to do error correction, because otherwise there is no point in saying that we are going to do computation if the computation is going to be erroneous. We know there is error in the system. But at this point, error correction is not available on quantum computers. So does that mean that we kind of sit idle and wait for that to happen in a few years? Not really, because really great works are already happening on a quantum computer, even though there is no error correction, and people are still fighting with noise, getting very nice results on the quantum devices that are at par with the best classical algorithms. And there is already a war going on whether quantum is giving better or classical is giving better in certain scenarios. So how they are doing it actually? and how can you do it? So this is the topic for today, that before error correction, how do we fight with noise? And we will not go to this beyond. I'll touch upon it if time permits, what this beyond means, but we will mainly stick to suppression and mitigation. So these are two techniques called error suppression, error mitigation, that helps us to work accurately with current quantum devices, even though error correction is not available. So let's get started. And these are kind of what I want to cover today, but my goal is not here to kind of bombard you with a lot of information. So what I will try to do is, after every of this section, stop and see if you have questions. Please feel free to ask questions, and I'll try to answer as far as I can. Um, let this be interactive, and let it not be just me talking and giving you a lot of information. The goal should be that you should be able to go back and be able to implement these methods in whatever applications that you are interested in, whatever applications that you are working on. Uh, okay, so let's get started, and let's get started with a very simple question. What can we do with a quantum computer? So the answer is very simple. In a quantum computer, we have a quantum circuit. This is an example quantum circuit, nothing very particular. We have a quantum circuit, and we run the quantum circuit on a quantum computer. We know that quantum computing is probabilistic, so we need to run it multiple times, and this multiple times is called shots. So when we run it multiple times, we get multiple bit strings, and from there we can build a probability distribution of outcomes. So this is what we can do with a quantum computer. And the second thing that we can do with a quantum computer is we can calculate the expectation value of some observable. Now, these 2 points, these two are not independent of each other. It is not like that you can get a probability distribution in some way, and in some other way you go and calculate expectation value. That is not true. I'll show you exactly right now how you can do it. But uh, these are the two things that we do. First, we can get probability distribution. Examples, Shor algorithms. The very famous algorithms, Bernstein, Vazirani, Grover, Shor, the famous algorithms that we know of, they require the distribution outcome, quantum phase estimation, quantum Fourier transform. All of these algorithms require the final distribution of the circuit, the final bit string coming from the circuit. Because in Shor's algorithm case, the bit string is the uh, thing that is going to tell me what are the factors of a given number. Um, in Grover's algorithm, the bit strings are going to tell me at which location a particular element is in a database. In quantum phase estimation, the bit string is going to give me the phase of the system, and so on. On the other hand, there are so these are the bit strings that we need. On the other hand, there are many algorithms. Let's say quantum machine learning, right? What we want to do, let's say I want to improve the accuracy, F1 score, something. This is a number. This is not a bit string, it is a number. Let's say I am looking into a chemistry problem. I want to find out the ground state energy of a molecule. It is a number, it is not a bit string. Optimization problem. I want to find out some graph property. I want to find out what is the size of the vertex cover of this, what is the size of the maximum independent set. These are some numbers again. So there are several examples that you can think of where eventually what you need is a number, and that number is what we are looking for. So that is what the expectation value is. This is a probabilistic method. Of course, quantum computer is a probabilistic, quantum computing is probabilistic. So if we run it multiple times, we are able to place. Okay. So if we run it multiple times, we are expected to get some different outcomes. So we calculate the expectation value, and the observable is something, this will sound like a cyclic definition. Observable is something that we can observe. For example, in physics, we can observe the momentum of a system, we can observe the energy of a system. So that directly goes into physics problems, chemistry problems. If you are thinking of graph property, say the combinatorial optimization problems that I was talking about, we need to build an observable whose expectation value will give me, say, what is the vertex cover, what is the set cover, things like this. If we are doing machine learning, we need to have an observable whose value tells me the F1 score, whose value tells me the accuracy, something like that. So whatever we are going to measure, we need to build an observable around that. And the expectation value of the observable is what we are interested in calculating here. How do we do that? So just one slightly mathematical example. It's not a problem if you don't follow this. It won't be a problem to follow the rest of the talk. So if we say that psi is the outcome of the quantum circuit, so say this is my quantum circuit, and the outcome here is some state psi, then the mathematically speaking, the expectation value is calculated like this, where O is the observable. Now, how do we do it physically? Physically, we can always write an observable because mathematically an observable is a Hermitian operator. So a Hermitian operator can always be written down as as the summation of some Paulis. So the CP are coefficients and P are Paulis. Now what we do is, so you see this psi o psi is essentially becoming like this. So you use a quantum computer to calculate this, and this summation and multiplication we do classically. This is how we calculate expectation value. So that's why I said that these two are not independent of each other. When you want to calculate this portion, you again need the probability distribution. You calculate this portion from there. Then classically, we sum and multiply this part. Now, why am I emphasizing so much on this kind of thing? Why am I spending so much time just to explain this part? The point is that whenever I talk of error mitigation, this we will discuss in detail later, but this is something very, very, very important. Whenever we talk of error mitigation is applicable only for problems of this type. So if you are going to deal with, say, Shor algorithm, Grover algorithm, quantum phase estimation, Fourier transform, blah, 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 so many algorithms, which eventually require the probability distribution, error mitigation at this moment is not applicable there. But if you have a problem, chemistry, ground state energy, physics, some properties of some state or something, graph theory, some properties of graph or something, machine learning. So all these kind of things, you can formulate it as a problem where you want to calculate the expectation value of observable. And this is where error mitigation starts uh, to play a role. So this portion, error mitigation not applicable. This portion, error mitigation applicable. What does this mean in another sense? If you are interested in, say, quantum cryptography, say, quantum communication, error mitigation is not applicable directly there. Why not? So when I am say when I'm doing a communication with you, you want to know the exact bits that I sent you. Not you don't want to calculate expectation value of the bits that I have sent you. You want to know what I sent you. So it falls under this kind of problem, not observable kind of problem. When you have cryptography, quantum cryptography, you end up with having some, I'm sending some bit strings to you securely. You want to get the bit strings. There will be some encoding, the bit string goes through a noisy channel and then you decode. You want to get the bit strings back, not some expectation values back. So whenever you are going to think of error mitigation, the first and foremost thing that is very, very important is whether the problem falls here or here. If here, doesn't work, error mitigation. If here, it works. So let's go ahead and uh, let's look into a quantum computer. Yeah, this is a figure a picture of a quantum computer. This is IBM Shadebrook. It is no longer active at this moment, but it was active even a few months back. This is a 127 qubit Eagle device, and perhaps you know all these, but these are the nodes here indicate the physical qubits, and the connectivity indicates that this node, this qubit talks to this qubit. What I mean when I say talks to this qubit, it means that if you have a 2 qubit operation, you can do the operation between 117 and 118 directly, but not between 117 and 110 directly. Of course, there is a whole bunch of studies on transpilation and everything, that how do you map your quantum circuit to this hardware map so that the talking is better and all. I won't go into that today. What I want to focus on is this color code. The way the color code is given is lighter the color, higher is the noise. So you can see all these different types of noise here. Read out. So when you measure, we will again go into deeper of this. When we measure, we get some noise when we measure. Uh, H error rate, this is basically Hadamard error rate, but you can think of it as single qubit error rate. Whenever you have single qubit gates, Hadamard, X gate, SX gate, any of those gate, this is the probability of error that you can expect. Whenever you have 2 qubit noise, you can expect this kind of probability. Two things to note here. First, there is error, true. Second, which is again very important, the error is not uniform. So you see most of the qubits here are pretty good. They are pretty dark and all, but there are some qubits, say this, which is very, very erroneous. And this you can understand from here also. You see all the things are going like this suddenly. Here also, suddenly, some of the qubits are very noisy. In fact, I remember there was a paper that the title of the paper was not all qubits are prepared the same. Anyway, but this is what we want to focus on. First, there is noise, and the noise is not uniform. These are two very important factors that will come into play. Now, the question is, um, if you have noise, you should be able to do error correction. This is the IBM roadmap that we have at this moment. And you can see that error correction fault tolerance, they come at 2029. So around 4 years or 5 years from today, you can start to have fault tolerant quantum computers. And then you can do error correction, run all those quantum phase estimation, Fourier transform, all those things. Um, but that doesn't mean that up to 2029, we sit idle. No, because there has been tons of papers and people are not sitting idle. What are they doing? They are doing error mitigation. So this error mitigation basically goes up to here. So they are doing error mitigation. Now, having said all these things about, let's come and ask ourselves, what is mitigation? What is suppression? What is correction? What are the differences? So let's look into correction first, because that's the easiest to understand. When we think of error correction, what happens? Errors are detected. First, we need to know that an error has happened. We need to know where the error has happened, which qubit the error has happened, and then we need to know what type of error has happened. Once we know all of these, we can correct the error. As simple as that. That is error correction. Now, when we do error correction, we can actually suppress the error rate to any arbitrary level that we want. Of course, by spending a lot of resource. So that's the third point. It has a lot of overhead, and that's why error correction is still not available in hardware. Um, so, but ideally, this is the case where we are going for, where we are thriving for 2029, the goal. But in the meantime, let's come to error suppression first. So here, errors are suppressed during execution but never detected. For example, for example, just a simple example, if I ask you that you need to place a qubit, where will you place 62 or 63? Definitely 62, because 63 is more noisy. So you don't need to detect whether an error is happening on 63 or not. I'll just avoid it to start with if I have the choice. Of course, I always may not have the choice, but if I have the choice, I'll avoid 63. So this is just a simple example that we don't really need to detect whether error has occurred or not. I'll just try to reduce the effect of error even without knowing this. By doing this, we can, of course, improve the quality of execution, but error correction, we cannot suppress it to any arbitrary low level. Because for example, if the 62 is also erroneous, right? There is also probability of error on 62. Why am I choosing 62 over 63? Because this has less probability of error. This has higher probability of error. I am not correcting the error. So even if I choose 62, there is chance of error happening, which I cannot suppress to arbitrary level. But I can reduce the probability of error by selecting 62 and not 63. So that's what suppression is. And of course, there is no extra qubit required for this. No extra runtime on quantum hardware is also required. I mean, why do we need extra qubits or runtime to select 62 over 63, right? But what is mitigation? So these are, I mean, it is mitigation and suppression. I won't say that the division is very strict, but there is a division, and this is the main division, that you can model the error and then remove them as a post-processing step. This is the same as you can see that we can improve the quality, but cannot suppress it to arbitrary low level. Here also, no extra qubits are required, but the runtime is increased. You need more hardware access to do error mitigation. So I would say not this one. This one is the main criteria by which we uh, separate between mitigation and suppression. But again, that is not like something very, very important. We can take these two on blue as one chunk versus correction. So how do we deal with noise now, not in 2029? So a simplified view is, for first, if we want to deal with noise, let us know our enemy first. If we want to fight the enemy, let us know the enemy first. What are the types of noise that we have? Well, lots and lots. I mean, we can't even list down everything here, but something very common: depolarization, over rotation, T1, T2, crosstalk, state preparation and measurement, all of those. So if there are so many types of noise, then we need more than one methods to deal with them. Like there is no one technique that will fit all of them, right? So one of the things that we do, I won't go into this today, most likely, which is called dynamical decoupling, which takes care of T2 and crosstalk kind of error, reduces the effect. Whenever I say take care of, it reduces the effect. Now, starting from after you do dynamical decoupling, starting from here, we do coherent over rotation, T1, T2, crosstalk, spam. There is something called twirling. We will go into these. So don't worry if these terms are not known to you. After we do twirling, for state preparation and measurement, we have something called measurement error mitigation. For the other kind of things, beyond twirling, we have certain things called zero noise extrapolation, probabilistic error amplification, and so on. So let's start from the outside and slowly start moving inside. Um, and we will see how these things actually work, what they are. Let's start with zero noise extrapolation. So, okay, any questions this far?
Hello, sir.
Yeah.
Actually, my question may be something might happen to be off track, but it is with respect to noise with digital image processing. So,
Hmm.
can you just understand my question and revise a bit with respect to quantum computing or quantum tech? Okay. So, my
Okay.
question is, in digital image processing, if there is a noise, it is might be considered to be an outlier because it is distorting the image or getting
Hmm.
some dot on the image that is what can I say, uh, distracting. It may be finding some distracting with respect to noise. Okay, so with respect to that, sometimes for digital image processing techniques, noise might be helpful or not be helpful. Means sometimes we kept the noise for blurring purposes or say some special operations. So with
Hmm.
respect to that, uh, in this scenario, in quantum scenario, are you gone through any particular case where noise is important for further process and you kept it without dealing with it? Means,
Yeah. Yes. So there are two things that I can talk about. One I can talk in a bit more detail. One I cannot talk in a bit more detail. That's a client project. So there is some projects ongoing even beyond this image processing in the fields of physics and all, where using noise you can do certain things. So those kind of things are definitely there. And if the problem is certain something like that, we don't want to do error mitigation or even error correction because noise is helping us. Having said that, the other example can be that you see this coherent over rotation. So coherent over rotation is something like, all quantum gates are unitary. So it's basically a rotation. So over rotation means that I ask the system to rotate say by angle theta, and it does some angle theta plus delta theta. But there are certain algorithms like the variational algorithms where you go around again and again. So these kind of noise, the variational algorithm can learn. So it can actually learn that, okay, when I say theta, the system means theta plus delta theta. So maybe if I want it to apply theta, I should tell it theta minus delta theta, something like that. So there are certain algorithms which can learn some noise, not everything. So, in general, mitigation is useful, but the question that you were asking, that there has been examples where noise helps. If that is the case, then definitely don't go for any of these. Yeah.
but sir, if we doesn't do error mitigation, but
Hmm.
that particular noise is affecting our time complexity of quantum system, then our means the model will be expensive, no? With respect to computational complexity or
Not really, not really. Because your computational complexity is kind of given by the circuit that you have. So if you have a circuit like this, what
Hmm.
we expect is that these are ideal noise, but actually these are followed by some noise channel. So there is no computational complexity increase due to that. It is just a property of the system at this moment.
Okay, means once the quantum circuit is fixed, it is considered as standard, and we go through till and with respect to it. That's
Yeah,
right, no?
yeah, exactly.
Okay, okay. Thank you, sir. Thank you.
Anything else on this? Okay, if not, let's get into this thing called zero noise extrapolation. In short, it is written as ZNE. So ZNE, if you look into ZNE, every time I see ZNE, it sounds so simple. The idea is so simple. I always feel like that I should have been the one to discover this. So the idea is that we know we have a circuit and the circuit has some noise that we cannot help. So let us say that the noise in the circuit is parameterized by some number. Let this be a number. Let us not fix any physical interpretation of what is lambda 1, how do you calculate lambda 1, all these questions we will avoid. We will just bypass all these questions and say that let us not worry about all of those. There is noise associated with the circuit, and I am calling that noise lambda 1. That's all. Now, let us, and this we will call as noise factor. Let us create a set of noise factors, lambda 1, lambda 2, so on. How do we create this set of noise factors? This we will come to. But for the time being, let us assume that we can create these noise factors. And this is the noise factor associated with the original circuit. Now we calculate the expectation values for each of these cases. Remember, whenever we change the noise factor, we ensure that the functionality of the circuit doesn't change. So, so what I mean when I say lambda 1 versus lambda 2 is that if there were no noise, this circuit and this circuit were functionally equivalent. But since there is noise, this circuit has lower noise than this circuit. This is what I mean. And in the next slide, we will see how to do something like this. But let us assume we can do that. Now we calculate the expectation values for these different lambdas. What does this mean? Now we have some data points here corresponding to lambda 1, lambda 2, lambda 3. We have some data points. So now we just fit it with a curve and extrapolate it back to lambda equal to 0, this point. What it gives, so this is something, again, something very important, is error mitigation does not remove the noise in the system. As you can see, I haven't done anything here to remove the noise in the system. I have fitted a curve, extrapolated it, and this E star gives me an estimate of how the system would have been, how the result would have been if there were no noise. So this is something, again, very important. I have seen many people mess this thing up, that mitigation is removing noise in the system. Not at all. All it is doing is giving me an estimate. If there were no noise, how do you how the result would have looked like? This is what mitigation does, and this is what it is doing. So as you can see, it previously I only needed to run one circuit. There was noise. Now I am running 3 circuits, or you can run k circuits here. So the quantum overhead increases. Instead of running one circuit, now I am running k circuits. So I need a higher quantum overhead. Plus, there is a classical post-processing step, which is like fitting the curve and then doing the extrapolation. So there is some increase in resource, both the quantum resource as well as the classical resource here. There is an underlying assumption, and we won't talk too much about this. If we can go into twirling, that's where we will talk a bit more about it. But the underlying assumption is that the nature of the noise remains same with increasing lambda. So yeah, there is a question.
Hello, sir.
Hello, hello.
With respect to my previous question, I got another question. You say that if the noise is useful, we don't do error mitigation, right?
Mhm.
But if we have a mixture of noises, say spatial noise or some frequency noise like that, with respect to digital image processing, I am talking itself. But
Mhm.
say we have mixing of noises, and one of them is useful and one of is not. Means one of is affecting and one is not. So if is there any process so that we can only laser point the affecting noise in a bad manner and
No,
mitigate
in
that
general,
only?
not. In general, not. Like the methods that I am describing here will kind of mitigate the effect of all sort of noise. If you need something like that, that will require some special treatment, some special study, how to do that and everything. So that is
So
not
this,
trivial.
the scenario with respect to my question may arise in the real time scenario, right? Means it might be
Mhm.
happen that there is a mixture of noises with some bad and good noises with respect to our model. It might happen, no?
Yeah, yeah, yeah. It can happen. It can happen.
Okay,
Definitely.
okay. So we have if want to deal with, we have to give some more efforts to address that particular scenario,
Yeah,
right?
yeah. Right, right. It is not
Okay,
trivial. Yes.
okay, sir. Thank you.
So yeah, the nature that the assumption that we have that we will kind of bypass uh, right now is that the nature of the noise doesn't change when I increase this lambda. Let's have that. So we will ask the first question: how do we create these circuits with different values of lambda? One method for that is gatefolding. So what does that mean? Each of these gate U is unitary, right? We know from quantum computing. So if it is unitary, the inverse of that is also the complex conjugate dagger of that. So the inverse exists. So if I replace a gate U1 with U1 dagger U1, functionally I have done nothing, because say U1 dagger is identity. Um, so effectively I am doing only U1. Functionally, I have not done any change. I could repeat this many times. So I have repeated this, say 3 times. I could have repeated this 5 times. As many times as I repeat U1 dagger, nothing happens. So this circuit and this circuit are functionally equivalent. We won't go too much into this mathematics, but let's try to understand what happens here. So, uh, great. These circuits are functionally equivalent, but we know that the gates are noisy. So when I replace one gate with three gates, this circuit is more noisy than this circuit. Similarly, if I replace one gate with five gates, this circuit will be more noisy than this circuit and this circuit. So this is what we will call lambda equal to 1. This is what we will call lambda equal to 3. If I repeat it with 5, I'll call it lambda equal to 5, and so on. So that is how we create the lambdas, the lambda 1, lambda 2, the things that we talked about. This is how we can create the lambdas. So it's very simple. This is called gate folding. Once we have that, how do we choose which kind of curve to fit with? In general, if we think of a depolarizing noise, it has an exponential nature. So exponential curve is the most natural choice. But at the same time, in general, what happens is that when you do the fitting with an exponential type of curve, it is uh, highly sensitive to many things. So what is done is often we try to fit it with some other polynomial curves. So if you know that your circuit is small, then an exponential can be approximated with a linear. If it is slightly bigger, it can be approximated with a quadratic, and so on. So looking into the circuit, we decide whether we want to go for a linear extrapolator, quadratic extrapolator, cubic extrapolator, or a exponential extrapolator. But this is what comes from the natural nature of the noise. So very simple here. But when we want to do digital ZNE in practice, there are some good practices and some limitations, of course. So right now in current quantum devices, so you see what happens is that when we fold these gates, the depth of the circuit is also increasing, right? And when the depth of the circuit increases, the noise in the circuit increase, all of those things happen. So what is done in practice is, in general, only the 2-qubit gates are folded, not the single qubit gates, because currently 2-qubit gates are way more noisy than single qubit gates. So when it is like 100 times more noisy than single qubit gate, what we can come back and say that, okay, almost it seems U1 and U3 are don't have noise when I compare it with U2. This is so noisy compared to these two that these two don't almost have noise. Yeah, this is changing very rapidly with the recent Heron processors. It is no longer 100 times, but it is still almost 10 times more noisy. So in practice, the folding will not go from here to here. We won't fold U1 or U3. We will only fold U2. This is the practice that is done just to reduce the some overhead, nothing more. Now note that folding increases the depth of the circuit. This is obvious, right? Previously, it was a depth 3 circuit, 1, 2, 3. Now it is a 1, 2, 3, 4, 5, 6, 7, 8, 9, a depth 9 circuit. So it increases the depth of the circuit. Now imagine that the initial circuit is already very deep. So here is an example. Let's say that the 2-qubit depth of the circuit. So when I say 2-qubit depth, we mean is this is something where that gives us a lot of information here. As I said, 2-qubit gates are way more noisy than single qubit gates. So when I say 2-qubit depth, what I mean is that let us forget that there are single qubit gates. Remove all the single qubit gates. Now calculate the depth. This gives us a lot of information because this is kind of the major source of noise. So that's what is 2-qubit depth means. So let us say that the 2-qubit depth of the original circuit is 20. And now I have selected lambda equal to 5. So what happens? The depth of the folded circuit becomes 100. Say you select lambda equal to 7. Depth of the folded circuit becomes 140. What will end up happening is that these circuits become too deep that eventually what you are getting is white noise. There is no reliable signals that you are getting from these folded circuits. So any extrapolation that you do will be wrong here. if you are not even getting any practical noise out of the practical signal out of the system. So there is a solution to this called partial folding. Um, in partial folding, we go for lambda equal to 0.2. So that's why I kept saying that let us not try to put any physical interpretation of lambda. It is a mathematical quantity. Lambda equal to zero point 0.2 means that out of 10 gates, 2 gates are randomly selected and folded. So it restricts the increase in depth due to folding, and this makes ZNE useful for much, much deeper circuits. So we already have results where the 2-qubit depth is 60 and beyond, and we can still do ZNE and get very, very good result. But you need to do partial folding on those cases. There are certain cases, obviously, where ZNE doesn't work. Say if my ideal expectation value is very close to 0. Now let us assume that we have a depolarizing noise because it is easy to calculate, nothing else. So as the probability of error, sorry, this should be tends to 1. Sorry, as the probability of error tends to 1, the expectation value tends to roughly 0, something like that. So if the ideal expectation value without noise is already 0 and your noise is pushing everything towards 0. So see, why did we why were we able to do this kind of extrapolation? Because what we are thinking is that this is a negative value. Think of that. What we are assuming is that these things are going towards 0 slowly. Exponentially, it is going towards 0. Now, if we start with something that is very close to 0 and then we move towards 0, we don't really, there is not sufficient information where we can fit a curve and we can extrapolate. So the information there is kind of lost. We cannot use ZNE for this kind of problem. We still can use ZNE, but not that well that it will work for other problems. Like ZNE works really well for other problems. So this is something where zero noise extrapolation fails. Now, there are obviously some more issues with digital CAD. Otherwise, there wouldn't have been those other error mitigation techniques. One issue is that for bigger circuits, see, I mean, we eventually want to go to bigger circuits, right? I mean, it is good to start with, say, 5-qubit circuit, 10-qubit circuit, but these circuits we can already simulate on our classical computer. I can just sit with a laptop, use Qiskit and simulate those circuits. So why even bother to go to a quantum computer, tackle all this noise and everything for those circuits that we can already simulate? It doesn't justify anything. So of course, when we start, we always start small. We start with smaller circuits, but the eventual goal should be to go at least to 40 qubits and beyond, to the regime where simulation, brute force simulation is not going to work. That is where using quantum computer makes sense. So at that scale, what happens is that when I am going to use, say, partial folding, remember what it said is that you randomly select, say if it is 0.2, randomly select 2 out of 10 gates. Now let's say that you have a very big circuit. So this big circuit is placed here and you don't have a choice. You have to use 63 also, 62 also, because it's a big circuit. You don't have too much of a choice. Now, when you do partial folding, let's say I have done partial folding, and when I did the selection, I selected randomly this edge. I selected this edge and so on, and I got some result. Now I gave the system to you and you will try it out. Say, since it is random, you end up selecting this edge, this edge. What will happen? You will get a worse result than me, just because you ended up selecting worse edges than me. But this is happening randomly. So sometimes the result will be good, sometimes the result will be bad, and this is something that you cannot avoid. So this becomes slightly uncontrolled. So what do we do there? There is, to avoid this limitation, there is something called probabilistic error amplification. I won't go too much into details of it, but the idea of probabilistic error amplification is, instead of randomly folding each gate, we look into an entire layer. So we learn the noise model of layer. So when we look into layer, what is happening? Say this edge is good, this edge is bad. So if I randomly select this versus this, they make a difference. But when I look into that entire layer, these things are averaged out. So instead of folding each gate, I will fold each layer. So this kind of system was used in the utility scale paper from IBM that came out in towards the end of 2023, and many other papers have used that since then. So yeah, let's not go into deeper of PE. Just keep this in mind that this is why PE is required. Yeah. So if there are questions, let's look into those, and then we can go into twirling. Uh, okay. So if not, let's go into twirling then. So when we go into twirling, remember one assumption that I made, and I said that, okay, we won't talk too much about it right now. One assumption that I made was that when I am increasing lambda, the nature of the noise remains the same. This was a strong assumption. I kind of made you believe that this is very trivial. It is not. It's a very strong assumption. So all the different types of noise that we have looked at, depolarization or Pauli noise channel, T1, T2, all of them have an exponential decay nature. Of course, the decay rate is not the same. Uh, the decay rate is not the same for all of them, definitely. So, but you can still say that, okay, hello. Yeah. So you can still say that these all have an exponential decay nature. Perhaps we can still make a single exponential curve that represents all of them. That is still a strong assumption because the decay rate is not the same for all of them. But there is one noise model which doesn't even have an exponential nature. It is the coherent over rotation. So think of what is happening in coherent over rotation. I have asked you to so think of what happens when we look into over rotation. Um, I have asked you to do a rotation by theta. You do a rotation by theta plus delta theta. So you have moved away from the ideal scenario. Now let's say that you keep making this mistake again and again. What will happen? When we do a unitary operation on a vector space, it's a rotation. So as you do over rotation, you first move away from the ideal scenario. And then after some time, you actually get back again towards the ideal scenario because it's a rotation. So you first move away and then you kind of rotate and then you again come back towards it from the other direction, right? So if you keep on doing this coherent over rotation, this will have a sinusoidal or some periodic nature where you first deviate from the ideal outcome, then you again come back towards it, again you deviate, and so on. So this is not exponential. This is something very, very different. So what we will use here is something called twirling. What it does is that again, it keeps the circuit structurally or functionally same, but it actually massages the noise models and gives a single noise model out of it, which makes it very simple to actually study. And I have forgotten the name who said this, but he's with Google. So one of those engineers from Google, they made a statement as big as this, that today we can make quantum computers because something like twirling exists. If twirling doesn't exist, quantum computers are not possible. So a statement as strong as that exists. So what is the idea of twirling? It's very simple. Let's say that I have a gate G which is Clifford. So what is a Clifford gate? A Clifford gate is something that takes a Pauli and maps it to another Pauli. So what it means is that, let's say that this is G is a Clifford gate, P is a Pauli. If I want to take this P and put it here, it will change to some other Pauli, P prime, but it will be a Pauli. So that's kind of the big statement here, that if you take P from here and move it after G, it will become P prime, but it will still be a Pauli. So a Clifford gate maps a Pauli to another Pauli. Now what you can do is, when we say that PG is equal to GP prime, you can also say that, okay, I'll apply one more Pauli, the same P here, and then I have to apply here, they are equivalent. Now a Pauli is its own inverse. So when you apply a P here, these two P actually cancel each other out, its identity. So now what it means is that G is equal to PG prime. So this equation holds when G is a Clifford gate. This equation holds. And it is not for a single set of Paulis. There can be many Paulis. You come up with a P and we can calculate the P prime. So what is done here is that, let's say that we have a quantum gate. So we randomly sample Paulis. So here I have sampled, so this P need not be a single qubit Pauli, right? So here I have sampled ZZ, and you can calculate that the P prime for a CNOT gate here will be IZ. So this is equivalent. This entire thing is functionally equivalent to this. Similarly, here, this entire thing is functionally equivalent to this. This entire thing is functionally equivalent to this. Now, when we repeat this again and again, and we take the average of that, this behaves like a stochastic Pauli channel. So it has a very simple Pauli noise model, irrespective of whether you have coherent over rotation, whether T1, T2, all these things have different decay rates and everything. When you do this twirling and you take the average channel, it behaves like a single Pauli noise model. So now all these different noise models are gone. We end up with a single noise model. Remember, one small thing is that it seems that, okay, now you have to sample many times and you had to run a single circuit. Now maybe you have to run hundreds of circuits. How do you deal with that? That is not how Qiskit deals with it. The way Qiskit deals is, we know that it's probabilistic, quantum computing is probabilistic, so we have to run it for many shots. So say you decide that I am going to run for n shots, 100 shots. So what Qiskit will internally do is that, if you want to do Pauli twirling, what Qiskit will internally do, it will create 100 twirled instances by sampling randomly. So if you are going for 100 shots, they are not equivalent shots anymore. They are this Pauli twirled 100 scenarios. So say this is 1, this is 2, this is 3. 100 such instances are sampled, and you get the final distribution, which is the average. So twirling is performed like that. There is no overhead of twirling. So it's a error suppression technique, not a mitigation technique. Uh, Again, twirling is performed only over 2-qubit gates, because we kind of expect that the single qubit gates are way less noisy. And remember that when we are inserting these gates, they also have their own noise. I mean, we are getting a huge benefit out of it. That is why we are okay with having a bit more noise, but lower the noise, the better it is. So if it is a single qubit gate, in practice, it is not twirled. If it is a 2-qubit gate, that is twirled. So here is one final picture from one of my papers earlier. Here, what we show is that this is something called an MBL circuit. Let's not go into what that is. And as we increase the depth of the circuit, this green line is what should happen. This is the ideal value. When we do only noise, no mitigation, nothing, you see that this black is the value, and it is kind of deviating a lot from the actual green curve. when I do zero noise extrapolation without twirling, you see this is the purple structure, and I mean this is in no way mitigated, right? I mean perhaps you would go and say no, no, the black one seems better than this purple one. What is this purple one doing here? And you can actually see this type of periodic nature appearing here. What we were discussing, right? This periodic nature is appearing here. But at the same time, the moment I put in twirling, you see this is the blue curve. So this is actually better mitigation than the black noisy unmitigated one. Just one thing we won't go into this is that this is the stochastic Pauli noise channel that I was talking about, that with probability 1 minus p, the state remains unchanged, and then with probability px, py, and pz, one of the Pauli gates are applied. This is the noise model that twirling takes any noise model to. So it's a very, very, very important concept that is used in quantum systems. Yeah, okay. Let me stop and see if there are questions at this point. Okay, if not, let's go into this. The measurement error mitigation is the last thing that we want to discuss, and then I'll just point you to a notebook where you can actually try all of these things out. So measurement error is something very, very simple. It is as simple as saying that, okay, I ask you, did you understand this? You say, yes, I wrote down no. Or you said, no, I wrote down yes. Something like that, as simple as that. So we all know in this type of measurement error, this is basically classical. 0 goes to 1, 1 goes to 0. And there is a very nice representation of that. This has nothing to do with quantum. This is the binary symmetric channel where a 0 remains a 0 with probability 1 minus p and goes to 1 with probability p. And on the other hand, 1 remains 1 with probability 1 minus p. So it's kind of the same probability that 0 flips to 1, 1 flips to 0. But when it comes to quantum, remember, when I say that what is measurement error mitigation, you said something, I wrote something down, something else down. This is measurement error, not mitigation. Sorry, this is measurement error. But there is also something called T1 error. What is T1 error? When we prepare a qubit in an excited state and we leave it idle for some time and then we measure it, it has a natural tendency to decay and go down towards 0. Something very similar to radioactivity. So if you wait for some time small t, prepare it in the high energy state, wait for some time small t, and then you measure, you will see that the probability of getting the outcome 1 actually exponentially decreases. And this exponential decrease is parameterized something by called T1. This T1 is a characteristics of the hardware. Now, if we look into the Eagle processor, so a single qubit gate operation requires roughly 60 nanoseconds. 2-qubit gate operation requires almost 10 times of that, 533 nanoseconds. Measurement requires almost twice or even more of that. So this is a non-negligible time. And the T1 error, that the rough T1 of Eagle processors was 267 microseconds. And when you find this out, what is the probability of getting 1, you see it goes down to 0.99. So what it means is that when I have the actual outcome is 0 and I am writing it down as 1, it is because of measurement error. Because you said 0, I heard it wrong or I wrote it down wrong. If it is 1 to 0, two things that are happening. First, you said 1, I write it down as 0. The same thing that happened here. But the other thing is that the time it takes to do the measurement, it has a non-negligible probability of decay. And in general, what we see is that if the outcome is 0, the probability that I get the outcome 1, this is actually less than the probability that I get the outcome 0 when the actual outcome was 1. And roughly speaking, this is almost twice of this. Because in general, what we see is that the probability of the only measurement error probability is around the scale of 0.01. and we see that the error coming from T1 is also 0.01. So when it goes from 1 to 0, it makes it like 0.02. It almost makes it twice. So this is no longer a binary symmetric channel. It becomes an asymmetric channel when it comes to quantum. Now there is something called measurement twirling. So if you remember what twirling was, what we said is that if you have a Clifford gate G, then you can pad it with P, G, P prime. You can replace G with P, G, P prime. It remains functionally equivalent. So the same thing we can do on measurement also. What happens after measurement? This part is the classical portion. We get 0 or 1. So let us apply an X gate before measurement. So if the measurement outcome would have been 0, I have made it 1. If it would have been 1, I have made it 0. I will keep track of that I have forcefully applied an X gate, a NOT gate here, and classically I will change the outcome as a post-processing step. So if I do that, I haven't done anything to the measurement. This and this, they are they are functionally equivalent. This forget about noise at this moment. So what this is doing, the outcome, it is taking the quantum state, writing it down as a classical state. What I am doing, I am flipping the quantum state, writing the classical state, flipping the classical state again. So it's exactly the same. And this is called measurement twirling. What it does, why is this useful? What it does, if you see, is that let's say that the outcome would have been 0. It flips to 1, right? Now let's take the otherwise, it will be easier to talk. When the outcome ideally was 1, the probability that this gives 0 is actually higher. So if I change this 1 to 0, then it is no longer affected by T1 error. So it actually gets a lower noise here. On the other hand, if this was 0 and it was going towards 0, the probability of 0 to 1 was lower, but I changed 0 to 1. So now it is again affected by T1 error, and it is getting some higher, it is getting some extra error because I have changed this, right? So what it means is that when I do this randomly many times, sometimes the outcome would have been 0. I have forcefully made it 1 and made the probability of error higher. Sometimes the outcome actually was 1. It had a higher probability of error. I have flipped it to 0 and made the probability of error lower. So when I repeat this many times randomly, what happens is that the asymmetry coming from this probability of 1 given 0 and 0 given 1, that gets removed. Because sometimes 1 gets lower error, sometimes 0 get higher error, and when you average it, it kind of averages out, and this becomes a binary symmetric channel. So it kind of, when we have an asymmetric channel, dealing with that is a bit difficult. So when we come to symmetric channel, it becomes much easier. So this measurement twirling again is something very, very useful because it takes an asymmetric channel and maps it to a symmetric channel. Again, with no extra cost, because anyway, we would have been doing n shots, that means n measurements, and I randomly do this. Now, what we do in measurement error mitigation is something called twirl readout error extinction, and it has a very nice acronym, which is TREX. The idea is simple, is that first, we forget about the original circuit that we are interested in. We just start with a 0 and we measure. And when we measure, we apply this measurement twirling. So when we do this measurement twirling, on the empty circuit, there is nothing in the circuit. I don't care right now what the original circuit was. And when I do this, I calculate this term. So let's not go too much into what this term means, but I calculate this term. Now, so here is just an example. Ideally, if there is no measurement error, this term is expected to be 1. This term, in some sense, gives a scaling factor of how much measurement error is incorrectly scaling the outcome. So if there is no measurement error, this term should be 1. But here is just an example that I have taken 6 shots and there are some measurement errors, which makes this term 1/3. So there is a scaling factor of 1/3. Now I do the same, but with the actual circuit that I am interested in. Let you be the actual circuit I am interested in. I just again twirl the circuit and get the outcome. What it means, what am I doing here? What I am doing is I am calculating again the same term, but now for the original circuit. Remember, in measurement error mitigation, I don't really care about gate errors. Gate errors I am taking care of using twirling and zero noise extrapolation. Here I am only interested in is removing errors coming from measurement. So when I do this calculation, when I take this circuit and when I write down this term gives me a scaled outcome. The scaling is coming due to measurement error. But how much is the scaling that I have already obtained before by running empty circuit? So I know what the scaling is. So when I divide this by the scaling factor, I get the mitigated expectation value. The scaling goes away. So obviously this is probabilistic. I have taken just an example here with 6 shots, but when you increase the number of shots, this becomes very accurate and T-Rex is known to do wonder. I mean, you can remove more than 98% measurement error using T-Rex. So T-Rex is known to do wonder. So what we just learned, everything, how the pipeline goes. Well, the pipeline is that you first transpile the circuits. Now we want to go for zero noise extrapolation. So we need to amplify the noise. Remember lambda 1, lambda 2, and so on. So we do the folding and everything. We amplify the noise. Next, we calibrate readouts. So when I say calibrate readouts, it means that you run that measurement twirling on the empty circuit. So that is giving you the noise, that is giving you the scaling factor. So this calibration goes after that. Next, you twirl the gates. Now you actually execute the twirl circuit. You get many outcomes. You aggregate the twirls. That gives you a average channel, which is a Pauli channel. Then we calculate expectation value. Now we first mitigate readouts by taking the scaling factor and we average the twirls. We take the scaling factor, we divide by the scaling factor that mitigates the readout. And finally, we do the curve fitting and we extrapolate to zero noise. What you all might be thinking is that was a lot. Yes, I agree. If you are thinking that, I am with you. I totally agree that it was a lot. So uh, if you are going to run your own circuits from your own application, this is a lot to remember. So Qiskit has your back, as I said here, is that there is something called resilience level defined in Qiskit. And you can define your resilience level, say for some reason, as one of you were asking, that what if I don't want to mitigate noise? What if I want to keep the noise as it is? Then go for resilience level 0, no mitigation. Say you want to go for resilience level 1. So all it will do is mitigate the readout error, but not the gate error. So it will apply only T-Rex. And you can go to resilience level 2, which will do everything that I just told you about. So you don't need to really worry what is going on. Oh, I have to do all of this. I have to amplify noise. I have to calibrate readouts, twirl. Qiskit will take care of everything. All you need to do is to put in your resilience level. So before any questions or anything, let me just let me just show one thing here. This is I hope this is visible. So this is your one-stop thing that you should be going for, the quantum.cloud.ibm.com. Create an account here. You can create a free account. You get 10 minutes for free. And if you have not tried out the 10 minutes, try out the 10 minutes. I have friends who have completed an entire PhD project on 10 minutes. So, and 10 minutes is every month for every user. So 10 minutes is a lot. It is not like what will I do with 10 minutes. Um, Here, if you go below, you will see the tutorials. Go to the tutorials here, and this section contains some of the best quality tutorials you will get, and everything here is for free. Here, if you go to error mitigation, so let's look into this combined error mitigation options. So this is the tutorial that you can look into, that how do you combine error mitigation options using estimator. Um, Here, as you can do see that they have taken a efficient SU2 circuit. This is something very widely used in machine learning kind of problems, and sometimes also in chemistry. And this is the main portion that I want to come up with, that when we create an estimator, see, putting resilience level as 0, so no mitigation first, running a job without any error mitigation. Now, instead of saying that I will do resilience level 1, 2, that is something that you can do naively. Or if you want to mix and match, you can also do that. We haven't covered dynamical decoupling, but you can turn on dynamical decoupling, nothing else. You can turn on readout error mitigation, nothing else. You can turn on twirling, nothing else. And you can turn on everything, which is resilience level 2. This you can just even say resilience level 2. And as you can see the results, you see that this is the ideal outcome that we expect. And no mitigation, you see that the results are slowly getting better as you do more and more things. And in ZNE, we have the best result out of this. And this was for a 10 qubit circuit. As I said, that there is no reason why you need to look at 10 qubit circuits. It doesn't make sense to keep working on 10 qubit circuits. You could have just done that on a classical computer. Go beyond 40 at least. That should be the goal, that we want to go beyond 40. So here is a 50 qubit example that you can see. And they have done the same thing here again. No mitigation, dynamical decoupling, measurement error mitigation, twirling, and then zero noise extrapolation. And here you can see the results, that you actually can get pretty good result even at 50 qubits, and there are so many results at 100 qubit and more regime. So if you look into this utility scale error mitigation, this is the probabilistic error amplification that we didn't go too much detail into. And this one comes from the Nature paper that I talked about. So all these are there for free. Just go and give it a try, and it shows everything how to do all of those things that we discussed today. And here also you can see the results that that are happening. So yeah, I think I'll stop here. The final take home message out of this should be that error mitigation works. It works not only for small systems, it actually works for really large systems. Here you can directly see a system with 50 qubits. There are results on 100 qubits. Um, there are already these notebooks which you can download, run for free. There is no charge for these. You get 10 minutes free. Please use that 10 minutes. The 10 minutes is lot. And strive to go beyond that 10 qubit, 20 qubit regime, because that's where you can actually do things on your laptop. And no point in saying that, okay, I am seeing what noise will do there, what error mitigation will do there. Those are good starting problems. Those are good starting points and toy problems. The goal should be how these tutorials are made. We start small, scale it up. That's where quantum computing actually is expected to show wonder, and that's where quantum computing is happening at this point. Yeah, so I'll stop here. Thank you for your patience and listening to this. If there are questions,
Thank you, sir. I have one question.
yeah.
Any question from the participants?
Yes, ma'am. I have one question.
Okay,
Sir,
okay.
normally you said 10 bit, beyond 10 bit you go and work. Give one example what kind of problem I can use. For example, suppose I have 1 lakh names of the Tamil Nadu students. From that I want to search one name. Whether I can go for quantum computing or to store 1 lakh names, how to use quantum computer.
No, so there are two things, right? Not only 10 qubits. I am saying that go beyond 40, 30
Yeah,
qubits, go
yeah,
to
I
the
agree.
regime of
Why
40.
should I go beyond 20? What type of application I can go for
Yeah.
50 qubits?
So the example that you just talked about, that will be an example of Grover's algorithm. Grover's algorithm is not applicable unless you have error correction and fault tolerance. So those are not the applications at this point. Right now, the kind of applications that we expect, and those are the type of applications most of the people are working on. First is high energy physics. Second is chemistry, material discovery and everything that includes, and third, life science, healthcare and life science. Fourth is combinatorial optimization. So this type of optimization problems. And fifth, in that sense, is machine learning, quantum machine learning. But again, the topics that I discussed is that, say, parts of chemistry, parts of healthcare and life science, these are not independent of machine learning. Machine learning is a tool. The application domains are in general expected to be these four, broadly speaking. Of course, not restricted to these four, but
No, no, my point,
yeah.
sir. What is the input to the program and what output I can get it?
So which kind of problem are you
Now,
looking up out of
suppose
this?
in physics, material analysis or something like.
So recently there has been some studies in material analysis. Say you have a molecule, you want to find some energy of it when some phase changes occur and something like that. So the input to that will be, you need to take the molecule. There are many methods like Jordan Wigner and other methods where you can take the molecule information and encode it into a qubit information. So this encoding is important. How do you take a molecular information? How do you take a graph information, physics information, and how do you encode it? It changes from domain to domain. It changes from problem to problem. Once you have done that, then there are many different circuits which are known to work for these problems, or you can come up with your own circuits as well. And the output will again be a bit string from where you calculate expectation values of some observable that you are interested in. This will be the bird's eye view of the problems.
No, no, my worry is to start scratch level, I need to refer already who have done the program, and from that I have to understand and then I have to
Sure.
modify. Am I
Yeah.
right?
Yeah,
Yes, sir.
definitely.
Thank you, sir. Thank you, sir.
So, yes, that's actually a important point that you raised. So, I would say that go to this quantum learning point here again. The same IBM quantum cloud.ibm.com. Here, if you go to this, there is a learning point here. Again, all of these are available for free, and you can see all of those focus topics. If you are just start off with any of these fundamentals, basics, general formulation, all of these. If you are already slightly advanced, want to look at some particular use cases, machine learning thing, variational algorithm in general, applicable to machine learning, applicable to chemistry, many other things, particular chemistry. So all these kind of things are available here. So yes, start with these definitely, and they will take you from the scratch, from starting with 5 qubits, 10 qubits, to actually going to that regime where you can go beyond 40 qubits or something. So yes, please use this quantum learning platform.
Actually, we are the computer science guy, so we
Yeah.
want to know the fundamentals of physics and material science, and then we need to apply the quantum
Yes,
algorithm.
I mean, if that is the case, I would say that start with these three. These three are from John Waters. They are awesome. Like, they are awesome in the sense that they are mathematically involved and everything. It's not some hand waving kind of thing done here. So this gives a very strong foundation, and then maybe go towards these two courses: variational algorithm design and quantum chemistry with VQE.
Yeah, it's completely different from conventional computer from
Yes, yes, yeah,
quantum because we are thinking in conventional way, but entirely
yes,
is different.
yes, I
Okay,
agree.
thank you, sir.
Any other question from the participants? So, thank you, Dr. Mojumdar, for this excellent, insightful session. It is requested to send your PPT for the participant for
Yes,
further
yes,
study.
yes, I'll send it to you. Yes.
Okay, okay. So, thank you once again. This is the end of session 11. Now we will move to the session 12. The link of the session 12 is mailed to the participants. Please join in session 12 link.